Hello, everyone. My name is Min, and I'm here joined today with some of my peers, Elvin and Brian, and we are doing our project over track racing. So the motivation for our project kind of stems back to high school and our experiences in track and field. Elvin and I were big proponents in the track and field sport. And as college students now, we are exploring relational databases, and we saw an opportunity to combine our old passion for track and field with our newfound technical knowledge. One challenge we faced in high school was the lack of tools to efficiently visualize and analyze our performance compared to other runners. And we felt very limited in how we can learn and improve without detailed insights into average speed and momentum. And with our project, we really hope to bridge these two connections and form something really cool. So the goal of our project is to design a comprehensive database system that enables the animation of a track race, supporting real-time visualization and post-race analysis. So the system is intended for sports analysts, coaches, and track enthusiasts who want to analyze race dynamics and athlete performance.
So for our ER diagram and what we built our tables based off of, was based off of this diagram right here. As you can see, we have three entities, that being racer, event, and track. Each entity has its own attributes, and as you can see, we also have relationships between these entities, such as runs in and occurs on. Um, As you can also see in our events, we have the distance ran. So this is like the 100, the 200, the 400. The track has the location, the name, and the racer has just some attributes based on the racer. And our runs in relationship has the top speed of the racer and the total time that they ran in relation to that event.
So for our data sources, they were mostly arbitrarily made with randomized names with similar ages. The average speed was attained by doing some research and using the article "What's the Average Human Sprint Speed?" A statistical analysis by Amber Sayer. In that research, I found that runners came to about 6 meters per second, but I ended up choosing the average to be around 4 to better visualize the running as well, and I added in variations between 1.2 plus or minus for each racer. So these are our implementation high-level functions and queries. For this first one, we have the fastest time to get to 50 meters. Ended up being the sixth runner down there. You can see that was at the time during the animation where that runner got to the 50-meter mark, and it was before anybody else. We used aggregation in this one, and we found the minimum time for when the 50-meter mark, when X was equal to 50, was crossed, and that came out to be 8 seconds.
And for our next query, we wanted to look at the position of a racer at a certain time. The time we chose was 15 seconds. As you can see, we used a basic SQL query for this. We just looked at the racer. We just picked a random racer. For this, we chose racer ID number 45, and then we took the time, and then we joined the two. And the event we were looking at was also number one, so we used the event ID at number one. And then on the picture on the right, you can see where they are on the race at 15 seconds. The top is where they start, and at the bottom is where they are at 15 seconds. And the bottom left picture is the output that it gave after we ran the query.
So our last high-level function query seeks to find the name of the racer or racers with the highest top speed in the track one. To achieve this, we combine data from multiple tables in a nested query that stores information about racers, the runs in events and occurrences on track, and also we set track ID to equal to 1 in this case, and the output shown to the right displays the racer with with the highest top speed with the respective speed in meters per second. So in this case, it was Alex, and his top speed was 11.5 meters per second.
All right, and then here's the demo of the visualization for race one. Here we go through the animations of the MLPQ. We set the steps to 32 steps. We set the speed down to 98 to be more visually appealing. And with that, you can see the race is dynamic with how the racers go. Here I do it a second time through for another look at it. 32 steps and speed down to 98. You can see that the speed of the racers decrease and increase.
So in conclusion, we successfully designed and implemented a relational database that stores detailed information on participants, track details, and race events. This database efficiently handles position data for each racer and ensures smooth data retrieval and processing without lag. Um, Additionally, we also developed an animation system that visualizes this track race in real time, allowing users to watch the races unfold through the MLPQ system. With this, we added elements of realism through the fact that certain racers will speed up, then slow down a little bit through our piecewise functions that Brian explained a little earlier. And this provides an engaging way to observe race strategies, speed changes, and overall performance as they happen. Looking at the future, we hope to incorporate 3D models and advanced animation features for a more immersive experience. I know it's pretty difficult to get a gauge of the race when it's on a 2D plane, so we really hope that maybe implementing a 3D model might help get a better insight about our project and about the race in general. We also hope to integrate additional metrics such as heart rate and lap splits for deeper analysis and use predictive measurements to forecast performance trends and outcomes in the integration of machine learning. And lastly, transition from hard-coded data to real-time data integration, which allows live race tracking and immediate updates during animation.
That is the end of our presentation. Thank you for listening.